Today we're going to learn about simplifying and converting radicals. By the end of this video, you should be able to simplify radicals, and you should be able to convert between radical notation and rational exponent notation. First, let's take a look at a radical and identify the parts. So this symbol is called a radical. The number or variables inside the radical are called the radicand. And n, which could be any number, typically you'll see it as just 3 or a higher number, that is called the index. So we're going to simplify these radical expressions. Number one should be familiar to you. You're just simplifying a square root. So when we simplify square roots, we are looking for a perfect square that is a factor of the radicand, which in this case is 24. So if you think, what perfect square goes into 24? That would be 4. 24 can be split up as square root of 4 times square root of 6, because 4 times 6 is 24. Then you should know that the square root of 4 is 2, and there's nothing else you can do to simplify the square root of 6. So we can just leave our answer as 2 square root of 6. We've done quite a bit of this in the quadratic and polynomials unit, so that one should be familiar. Higher degree radicals are a little more challenging. When we're trying to simplify a cube root, we're looking for a perfect cube that is a factor of 81. So we're going to look at this power sheet, and if you don't have it already, you'll get it when you get into class. So the perfect cubes are this third row here, where they're all a number to the third power. So we want to see if any of those are factors of 81. And 27 times 3 gives us 81, so we're going to use that. So I can split up cube root of 81 into cube root of 27 times cube root of 3. Going back to the power sheet, 27 is 3 cubed, so when we ask for the cube root, we are saying what number cubed will give us 27. So the cube root of 27 is 3. And then I can't do anything to simplify the cube root of 3. So when we have a fourth root, it's the same idea. We're looking for a perfect fourth power that is a factor of 72. So if I look at the next row, we can check 2 to the fourth, but 3 to the fourth is bigger than 72, so that's clearly not it. So we can check and see if 72 has 16 as a factor. That does not go evenly, so that means we're not going to be able to simplify the fourth root of 72. So we'll just leave it as fourth root of 72. We can also simplify radicals that have variables in it. So if I have fourth root of 243 x to the 15th y to the 8th z to the 9th, I want to look at each of those pieces individually. I'm going to look at fourth root of 243, see if I can simplify that. Then I'll look at the fourth root of x to the 15th, then fourth root of y to the 8th, then fourth root of z to the 9th. So let's start with what we know, which is the numbers. So I'm going to look and see if there's a perfect fourth power that goes into 243. So looking back at the power sheet, I need a factor of 243 that is in the fourth power row. So I'm looking at 16 and 81. 243 divided by 81 is 3, so that's what we're going to use to simplify this. So I can split up 4th root of 243 into 4th root of 81 times 4th root of 3. And the 4th root of 81 is 3. So that's the number part of the simplifying. When we simplify variables inside radicals, I'm going to write out the long way and then I'll show you the shortcut. So if I have x to the 15th, that means I have 15 x's. So when I'm trying to take the 4th root of it, that means that I'm looking to see how many sets of 4 can I make and how many are left over. So I have a set of 4, a set of 4, a set of 4, and then I have 3 x's left over. So those of you who liked simplifying radicals using the factor trees, it's the same thing even when you have variables. So we're essentially just writing out a factor tree for x to the 15th. So that means I have 3 sets of 4. So that means I can write an x cubed outside the radical, and then I have 3 x's left over. And then I have 3 x's left over, so I'll write those inside the radical. So the shortcut for doing this is if I take 15 and divide by 4. I end up with 3.75. So that means I have 3 and then 3/4, or a remainder of 3. So the fact that I have 3 as the whole part of that fraction means that I have an x cubed that's going to go out front, and the leftovers, so the remainder 3 or the 3/4, are what's going to go inside the radical. So let's try the next one with y's. We have y to the 8th. If we divide 8 by 4, we get 2, and there's nothing left over, which means that the 4th root of y to the 8th is just y squared. So I'm going to start writing out all of these as the answers. So from the 4th root of 243, we have a 3 that's outside the radical. From the 4th root of x to the 15th, we have an x cubed outside the radical. Then we just said the 4th root of y to the 8th is y squared. Then inside the radical, we had a 3 inside the radical, we had an x cubed inside the radical. We had no y's inside the radical because there were no leftovers when we did 8 divided by 4. When we take the 4th root of z to the 9th, if we do 9 divided by 4, 4 goes into 9 2 times, and there's 1 left over. So this will be our final answer. Let's try one more example. We have cube root of 24 x to the 6th, y to the 4th, z to the 7th. So let's look at cube root of 24. What perfect cube goes into 24? We look at the cube row. 8 is a perfect cube that goes into 24. So I know that cube root of 24 can be rewritten as cube root of 8 times cube root of 3. Then we know that the cube root of 8 is 2. So cube root of 24 can be simplified to 2 cube root of 3. So let me write this out. When we do the cube root of x to the 6th, we divide 6 by 3, which goes evenly. 3 goes into 6 2 times with no leftovers. That means we have an x squared outside the radical and no x's inside the radical. For y to the 4th, 3 goes into 4 once with 1 left over. Cube root of z to the 7th, 3 goes into 7 twice with 1 left over. So when we're simplifying radicals, we need to think about basic division that you learned in 3rd or 4th grade. How many times does 3 go into 6 and how many things are left over? Now, the other thing that we're going to learn today is how to convert between rational exponent notation and radical notation. So, rational exponents are fraction exponents. An nth root of a, written as nth root of a, where n is the index, would be rewritten in rational exponent form as a to the 1 over n power. So whatever the index of the radical is, that will be the denominator of the rational exponent. Let's look at a to the m over n power. We just said that the index is the denominator. So I know that n will be my index, and a to the m power will be inside the radical. The other way we could write this is the nth root of a, all of that to the m power. Those are equivalent. As long as n is the index, m can be the exponent of a or the exponent of the entire radical. So we're going to rewrite these using exponent or radical notation. So if it's in rational exponent form, we're going to convert it to radical form and vice versa. So we have 7 to the 3/4 power. Remember that the denominator is always the index. So we could write this as the 4th root of 7 cubed, or the 4th root of 7 all to the 3rd power. Now, number 2 is a little tricky. We have two terms with rational exponents, but they have different denominators, which means they're going to have different indices. We want them to have the same index. So I'm going to make them have a common denominator. That way they have the same index. So when we think back to elementary school when we did common denominators, if you have 1/3 and 3/4, you want to find a number that both 3 and 4 go into, which is 12. So if I want to make 1/3 have a denominator of 12, well, I have to multiply 3 by 4 to get to 12, so I need to multiply the numerator as well. To make 3/4 have a denominator of 12, I need to multiply by 3 over 3. So after rewriting this, I have x to the 4/12 and y to the 9/12. So when I write this in radical form, my index is 12. I have x to the 4th y to the ninth. For number 3, we have the square root of 13 to the 6th power. Now, square roots can be a little bit tricky because the index is not written. Square root has an index of 2. So when you write this, you have 13 to the 6 over 2 power. Make sure that the index is the denominator. And you can simplify this to be 13 cubed, which, if you type that in your calculator, 13 cubed is 2,197. The next problem is the cube root of x to the 6th, y to the 7th. Remember that the index becomes the denominator. So you have x to the 6 thirds and y to the 7 thirds. 6 thirds simplifies to 2. So we have x squared, y to the 7 thirds.